This is Dr. D. Govardhan, Professor in the Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. The today topic is problem solving on moment, Varignon's theorem, and couple. The moment. Generally, the moment of force is it is having effect when the force is acting on a body. When it is having an effect of to turn the body in clockwise direction or an anti-clockwise direction, is treated as movement. That is the tendency of a rotate of a body in clockwise or anti-clockwise direction is treated as a movement of a force. Here, these movements are classified into two types now. One is clockwise movements and the second one is anti-clockwise movements. So, when they are finding the resultant of movements or the forces in that process, the clockwise movements generally are treated as positive movements and anti-clockwise movements are treated as negative movements. Here in the figure now, shown in figure, it is treated as clockwise movements. These clockwise movements is generally treated as a positive while doing the calculations. That means it is a movement of a force whose effect is to turn the body or rotate the body about the point in the directions in which the hand of clock rotates. That is treated as the clockwise directions. This is treated as a positive momentum. If you take the forces here now, F1, F2 and F3 forces are acting. The moment created by these forces F1, F2, F3, at O we are taking now. O point, assume. This F1 tends to rotate the body in clockwise directions. F2 also tends to rotate the body in clockwise directions. And F3 also rotate the body in clockwise directions. Hence, the movements created by the F1, F2, F3 at a point O is treated as a positive movements. That means they are tending to rotate the body in clockwise directions or in the directions in which the hands of a clock is moving now. Anti-clockwise movements, generally these are treated as negative movements. It is a movement of a force whose effect is to turn the or rotate the body about the given point in the opposite directions in which the hands of a clock is moving now. Here example is, if you take a body in which three forces are acting now. One is F1 and F2 and F3 forces are acting as shown in figure. At O, the F1 forces tends to rotate the body in anti-clockwise directions. F2 also anti-clockwise directions and F3 also anti-clockwise directions. Hence, the moments created by these forces F1, F2 and F3 are treated as negative moments. So, in general conventions, while solving the problems, these clockwise moments are treated as positive moments and anti-clockwise moments are treated as negative moments. The Varignon's principle of moments. It is also called law of moments. It states that if a number of coplanar forces are acting simultaneously on a particle, the algebraic sum of the moment of all the forces about any point is equal to the moment of the resultant force about the same point. Here I am taking here one body there, here A and B. Here the forces are there now. One is acting downward direction, F1. The second one is again as in F2. One more force is acting like this now. That is F3. That is three forces are acting on a body. According to the Varignon principle, these are coplanar forces. F1, F2, F3 are the coplanar forces. That is, all are lie in the same plane now. It may be vertical or horizontal or inclined plane, but all the forces are lying in the same plane now. Okay, when they are acting simultaneously on a body, the algebraic sum of the moments of F1, F2, F3 about any point is equal to the moment created by the resultant force at the same point. So the main application of Varignon principle is it is to determine the resultant of parallel forces which are acting on a body. The resultant of two parallel forces, that means whose line of intercept is, whose line of action is not at all intersecting any point, can be determined by the principle of moments both in magnitude, direction as well as the point of applications. So the main application of the Varignon principle is it is to determine the resultant of parallel forces which are acting on a body as well as the point at which the acting can be determined. Okay, according to this figure now, here the forces F1 and F2 both are acting at O as shown in figure. The F1 is represented graphically as OA and F2 is represented as OB as shown in figure. According to the law of parallelogram of forces, the resultant of these two forces is representing by the R as shown in figure now. Now, the moments created by the forces F1, F2 and at R, and the moment created by the forces F1, F2 and the resultant R at O point, according to the Varignon's theorem, is given as R into R, that is the resultant force, and perpendicular distance between O and R is equal to small r, that is product of force into distance, R into R is equal to F1 into R1 plus F2 into R2, where F1, F2 is representing the magnitude of F1 force as well as F2 force, and R1, R2 is representing the distance between the O point to the forces F1, F2, the line of action of the forces F1, F2 measured perpendicularly. Using Varignon principle, the resultant of parallel forces and the point of application can be determined analytical method now. Here I am taking one problem now. Two unlike parallel forces of magnitude 400 newtons and 100 newtons are acting in such a way that their line of actions are 150 mm apart. Determine the magnitude of the resultant force and the point at which it acts. So according to the figure, two unlike parallel forces, unlike means the direction of the two parallel forces in opposite now, not in the same direction now. They are acting in opposite direction. Parallel forces but are acting in opposite direction. Two unlike parallel forces of magnitude 400 newtons and 100 newtons are acting in such a way that their line of action are 150 mm apart. Hence, I am taking just A and B are the points at which 400 newtons as well as the 100 newtons is acting, which are separated by 150 mm apart now. So, find the resultant of these two forces and the point at which it attacks now. Since the given forces are unlike and parallel forces, then the magnitude of the resultant force is given by magnitude of resultant force. It is equal to 100 is treated as positive and 400 is treated as negative. That is the resultant is equal to, which is equal to minus 300 newtons. Okay, the resultant force is equal to algebraic sum of the component of forces which are acting along the y directions now. Because all are only one direction, so vertical direction is there now. Algebraic sum means here now 100 is acting upward direction positive and 400 is acting downward direction negative. Hence, resultant is equal to 100 minus 400 is equal to minus 300 newtons is treated as a resultant of these two parallel forces now. So the second one is required. the point at which the resultant force is acting now. Let us assume x be the representing the point at which the resultant force is acting. So according to the Varignon principles, the moment created by the forces, which forces 100 newtons as well as the 400 newtons, at any point it is equal to the moment created by its resultant force at that point now. So which is equal to, here now, I am taking, let x be the already we have taken, is the distance from A, that is C point, at which the resultant force is acting now. Now according to the Varignon principle, the moment created by the resultant at any point, that is preferably I am taking A point now, that is R into x, which should be equal to the algebraic sum of the moments created by its components at that point now. So I am taking here now A point, A is our reference point. The resultant force, the moment created by the resultant force at A is equal to R into x. But it tends to rotate the body in which direction now? Along clockwise directions. Hence it is treated as positive now, which should be equal to the moment created by its components. Its components means 100 as well as the 400 newtons. That is 100 into the distance is given 150, but it tends to rotate the body in which direction now? Anti-clockwise directions. Hence it is treated as a negative, and 400 into 0, which should be equal now. That means according to these problems now, that is R into x is equal to, that is R is equal to 300 minus, it is nothing, 300 into x is equal to, we can take it as minus 100 into 150. From this relation, we can take it as x is equal to minus 100 into 150 divided by 300, which is equal to 50 mm. That minus sign is representing it is acting just toward the point A now. Okay, this is our answer now. So 50 mm, this is nothing but a text now. Similarly, the second problem, let us take a uniform beam AB of weight is equal to 100 newtons and 6 meters long, have two bodies of weights 60 newtons and 80 newtons suspended from its two ends as shown in figure. Uniform bar AB is given now of weight 100 newtons. That means the A weight is always passed through its center of gravity. Since it is uniform, it lies within the midpoint of the length of the bar. The bar length is given 6 meters, and so when you are measuring its distance from A, that is at a distance of 3 meters, that is the point C, the weight of the body is acting now in downward directions. And two bodies of weight 60 newtons and 80 newtons suspended from its two ends as shown in figure now. That means at A 60 newtons, B at again 80 newtons. That is the total number of forces is equal to 60 newtons, 100 newtons and 80 newtons that are acting now. Finally, analytically, the magnitude of the force and what point the beam should be supported so that it may rest horizontally. So first of all, we have to determine the resultant of all the forces. Here, it is a balance, nothing but the resultant force should be equal to 0 because the body should be kept in horizontal. That means one force should be kept in such a way that it should be equal to the resultant of these three forces but acting in upward directions. That is the treated as here balance of force or equilibrium, which is keeping the body in equilibrium conditions. Now, let here R be the assuming the force which is keeping the beam in horizontal directions, which is at a distance of x from B as shown in figure. Now, since the body is in horizontal position means equilibrium condition, according to the conditions of equilibrium, the sum of the component of forces which are acting along the x direction should be equal to 0. That is sigma fx is equal to 0 required. But the component which are acting along the x directions in this case are not there. Hence, this equation is not valid for this problem. The second equation sigma Fi is equal to 0. That is the sum of the component of forces which are acting in vertical direction should be equal to 0. While determining the sum of the component of forces in vertical directions, the component of forces which are acting downward direction are treated as a negative, upward direction are positive. Hence, here upward force are minus 60, minus 100, minus 80. It should be equal to minus, it nothing should be equal to 0, which means R is equal to 240 newtons now. So we got according to this conditions, sigma fx is equal to 0, sigma fi is equal to 0. We got that is the force which is keeping the body in equilibrium positions. It is equal to 240 newtons. But where it is acting now? Let x be the distance from B, where the R force is acting, which is keeping the body in horizontal position now. Hence, according to the Varignon principle, if I take the moments created by the component of forces at any point should be equal to the moment created by its resultant force at that point now. So, according to this one, since it is now equilibrium position, sum of the moments created by the all the forces must be equal to 0 required now. Because here now keeping in horizontal now. So, this moment should be equal to 0. Here with respect to the B point, 18 newtons, the moment created by the 18 newtons is equal to 0, since the distance is equal to 0. D at D, the R is tend to rotate the body in clockwise directions, that is the positive. At C, the 100 newtons, it tends to rotate the body in anti-clockwise directions, negative. And at A, 60 newtons tend to rotate the body again into anti-clockwise directions, negative now. That means here 80 into 0, assume this minus, plus R into X clockwise, minus 100 into middle point, minus 60 into 6, it should be equal to 0 we required. That is the sum of the component, sum of the moments created by the forces, 80 newtons, R force, 100 newtons, and 60 newtons must be equal to 0. Okay, by using these equations now, since we are taking the moments at a point B, hence the moment created by 80 newtons at a point B is equal to 0. That means the remaining forces are now R into X is equal to, we can take it as 100 into 3 plus 60 into 6 now, which is equal to 300 plus 360, it equal to 660. R is equal to, already we got which is equal to 240 into X now. Hence X is equal to 660 divided by 240. This is our required answer now. Okay, take it just whether the answer once again now, the procedure. The weight of the rod is given 100 newtons and the bar is uniformly, hence it is acting in the middle of the beam as explained earlier now. The body is supported by two forces at A and B, which is equal to 60 newtons and 80 newtons. Let X be the distance B, the point where the beam should be supported, or the resultant of all the forces are acting, but in acting opposite direction to keep the body in horizontal direction. Okay, according to this paper now, resultant force is equal to 240, already we measured. Now taking the moments about D is equal to we got X is equal to 660 divided by 240, which is also equal to 2.75 meters from B as shown in figure. This is the way generally used to find the resultant of parallel forces and the point at which it is acting by using the Varignon principle. In another problem, a horizontal line PQRS is 12 meters long, where PQ is equal to QR equal to RS equal to 4 meters. The forces of 1000 newtons, 1500 newtons, 1000 newtons and 500 newtons act at P, Q, R, S respectively in downward directions. The line of action of these forces makes an angle of 90 degrees, 60 degrees, 45 degrees and 30 degrees respectively with the PS. Find the magnitude and direction and position of the resultant force. So, here in order to find the resultant forces, this we are using three equations, sigma fx, sigma fy and the moment created by the forces at one point. So, first to resolve the forces, to find the resultant of these four forces, we required that is the x component of resultant force is equal to sigma fx and the resultant that is the y component of resultant force is equal to ry, which is equal to sigma fy, and theta is equal to tan inverse of ry divided by rx. This, we have to use these equations first to determine the resultant of 1000, 1500, 1000 and 500 Newton forces which are acting on a line PS. Now we require first sum of the component of forces acting along the x direction now. First force we are taking at P now, but it is acting vertically downward direction, so there is no x component. The second force at Q, 1500 newtons. It can be resolved into two components now. One is along downward directions, one more is acting along the negative x directions now at Q now. Similarly, the 1000 force at R, when it is resulted in two components now, that is x component is acting toward the left hand side and y component is acting in downward directions. The third one is again when you are resolving the forces, two components, again vertical component is acting downward directions and horizontal component is acting toward the left hand side now. The sum of the forces which are acting along the x directions, that is Rx is equal to sigma fx we require now. Okay, according to this problem now, 100 is the first 1000, the angle is equal to 90, that we can take it as cos 90. Again minus, because the second component 1500 is horizontal component is acting towards the left hand side, you have to take it as a minus sign, that is 1500 into cos 60 degrees minus, again third component minus 1000 into cos 45 degrees and fourth one again minus 500 into cos 30 degrees. If you take the component of all the forces, the obtained values are treated as the x component of the resultant force now. Similarly, the y component of all the forces which are acting on a line PS is equal to sigma Fy. 1000 newtons is the ultimate, 1000 newtons is the acting downward directions 90 degrees. We can take sin 90, but negative 9. Again minus 1500 sin 60, again minus 1000 into sin 45, again 500 into sin 30 degrees. All are acting in downward directions, hence they are treated as the negative values now. Now after getting the values Rx as well as the Ry, determine the theta values. Theta is equal to tan inverse of Ry divided by Rx. That is theta is equal to tan inverse of Ry divided by Rx. Determine this angle. Since x component as well as the y component both are here negative, means they are belongs to a third quadrant. That means here x component and y component both are negative now. That means it is acting in third quadrant. The inclination generally lies between 180 to 270 degrees now. Or here now we can take it as which is equal to, since both are negative are there now, you can take directly just with the angle which is made with the x-axis as shown in figure now. Now I am taking the problem once again now. The magnitude of all the resultant force we have determined. Result all the forces in horizontal directions. Sigma h is equal to, we have taken this is equal to, we got 1890 newtons now. Just after resolving all the forces vertically, that is 1090 plus 15,000 sin 60 plus 1000 sin 45 plus 500 sin 30, all are just acting downward directions now. Hence it is equal to 3256. We got it now after substituting the values of sin 90, sin 60, sin 45 and sin 30 degrees now. The resultant of all the four forces is equal to R is equal to under root of sigma h whole square plus sigma v whole square, which is equal to under root of 1890 whole square plus 3256 whole square, which is equal to 3765 newtons or 3765 newtons. We got it now. This is known as the magnitude of the resultant force. Now, the direction of the resultant force now, already I told now, tan theta is equal to sigma v divided by sigma h now, which is equal to 3256 divided by 1890, which is equal to 1.722 or equal to 59.8 degrees. Since we can take it in third quadrant, otherwise the resultant force is acting like this now, it is making an angle of 59.98 degrees like this now. Why? Because now when we are taking R is equal to theta is equal to tan inverse of sigma Fy divided by sigma Fx. Both are treated as a negative negative. This is nothing but cancel. You can put it in third quadrant or just by extending. Otherwise, just you can represent it directly in the first quadrant like that now. So we got the resultant of all the forces in nothing but making an angle of 59.8 degrees as shown in figure now. Now position of the resultant force now. Let x be the distance between P and the line of action of the resultant force. Then according to the Varignon principle, the moment created by the resultant force at P should be equal to the moments created by the forces which are acting at P, Q, R and S now. Let here now from P, this is nothing but assume this x is the distance between the P as well as the point where the resultant force is acting now. This resultant force again, it should be resolved into two components, vertical component and horizontal component. This vertical component only tends to rotate the body in clockwise directions. The x component, it will always pass through the along the lines PS as shown in figure now. That is, it is nothing but separated by 0 distance now. Hence, the horizontal components will not create moments when you are taking the point on line PS or just along the line PS as shown in figure now. Now, that means only we have to consider the vertical component of the forces, not horizontal components of forces now. Hence, the moment created by the vertical component of the resultant force at P position is given by 3, 2, 5, 6. This is treated as a vertical component of the resultant force into x be the distance between the point of application of the resultant force upon P equal to 32, 56 into x as shown in figure, which should be equal to the moment created by the forces. Which forces are acting now? 1000 force, 1500, 1000 and 500. Because here all are rotating, tends to rotate the body, clockwise directions. Hence, it should be equal, or otherwise you can take it as a positive also now. So, 1000, since at P, this 1000 force is acting now, hence the treated as 0, it is the distance now, plus 1500, that is second force, PQ, and here vertical component we have to take it now, only. That means vertical component is equal to, according to this figure, it is equal to 1500 cos 60. Third one is 1000 into cos 45 into 8. Last one is 500 into here cos, sin 30 into 12. That is when you are taking the moments at a point to P now. Here, assume just a resultant force is acting now. The vertical component of resultant force is there now. It is there. That is the moment created by the vertical component of the resultant force at P is equal to R into X. It should be equal to 100 into 0. The second one is 1500 into sine 60 degrees, that is vertical component, into 4, and into R 1000 vertical component we are taking, that is sine 45, distance is 8. At S point, the vertical component is equal to 500 into sine 30, the distance is 12. That is the moment created by the 4 forces of 1000, 1500, 1000 and 500 forces at P should be equal to the moment created by their resultant force at P now. Since we are not at all considering horizontal distance, because the line of action of horizontal component is passing through point P S line only, hence their effect is equal to 0, or moment created by that component is equal to 0. Hence we have to consider only vertical components to determine the position of resultant of that 4 forces now. So according to this problems, when you are taking now 100 into 0, 1500 into cos 60 into 4 now, 1000 into 0.707 into 8, and 500 into 0.30 into 12, which should be equal to 13,852, or x is equal to 13,852 divided by 3,256, which is equal to 4.25 meters. That is from P point to the resultant force is acting at a distance of 4.25 and making an angle of 59.8 degrees with respect to the x-axis. Now I am taking just one more problem now. A system of parallel forces are acting on a rigid bar as shown in figure. Reduce the system to a single force and a couple at a single force and a couple at B now. Here reduced to single force means These all the four forces are replaced by single force, which is treated as the resultant of all the forces now. Resultant of all the forces, which will having the effect of all the component of forces which are acting on a body A, B, C, D as shown in figure now. So given here the forces at A 32.25 newtons, at C 150 newtons, at D 67.5 newtons, at B 10 newton force is acting now. Similarly, the distance between AC is equal to 1 meter, AD is equal to 2 meters, and AB is equal to totally 3.5 meters is given now. Now, single force system, that means these four forces are replaced by single force now, which is having the same magnitude now. So, in this case, the 32.5 newtons of first force which is acting at A point, it is acting upward direction, so it is a positive force. At C, 150 newtons downward direction, so negative force. At D, 67.5 newtons force acting upward direction, so positive. Again at B, 10 newtons acting downward direction, so negative. Hence, the resultant of these four forces is equal to 32.5 minus 150 plus 67.5 minus 10, which is equal to 60 newtons. This minus is representing the resultant of force is acting in downward directions. The locations. Let x be the distance of the resultant of force acting toward the left side, toward the right side, as shown from here. Assume somewhere it is acting the resultant of force, assume, which is at a distance of x now. Like this now. Let x be the distance at which the resultant force is acting on a beam AB as shown figure now. Now, according to the Varignon principle, the moments created by the resultant force are at A should be equal to the algebraic sum of the component of forces which are acting on the body now. Both should be equal now. That is here now. Let O be the point. This is where the resultant force is acting now. It is at a distance of x from point A now. Now, according to this figure now, R into x now. That is the moment created by the resultant force at a point A equal to, that is distance is given x, R into x should be equal to the sum of the moment created by the forces which are acting at a point A, C, D and B now. Okay, at A 32.5, since the moment also taking at A only, the distance is at 0. At second 150 newtons, that is tending to rotate the body in clockwise directions, hence the moment is treated as positive, that is 150 into 1. Again at D 67.5, it tends to rotate the body in counterclockwise directions, hence it is treated as negative, that is 67.5 into 2 negative. Again at B, it tends to rotate the body in clockwise directions, hence positive, that is equal to 10 into the distance equal to 3.5 newtons now. Here R is also acting downward directions, hence the moment created by the resultant force at A is also in clockwise directions, hence treated as a positive now. So by solving these equations we got to, that is R into x is equal to minus 150 into AC means 1 plus 67.8 AD minus of 10 into AB now. From this relation we got x is equal to 0.833 meters now. That is 60x is equal to, we got how much it is now? Here minus of 60x is equal to, here now is a positive because it tends to rotate the body in clockwise. 150 is a positive, it is a negative and it is also positive now. From this relationship we got 60x is equal to minus 150 plus 135 minus 35, which is equal to minus of 50. Hence, x is equal to, therefore, x is equal to minus 50 by minus 60, which is equal to 0.833 meters. That means the resultant force is acting at a distance of 0.833 from A as shown in figure now. Okay, this is now treated as a reducing system of forces into single force. The single force means we have to identify what is the magnitude as well as the directions and point of application of the force. The second bit of the problem is a single force and a couple at A now. That is here according to the figure now, AB the length of the beam is given, which is equal to 3.5 at a distance of 0.833 meters. The resultant for R is equal to 60 newtons is acting now. Your total distance is given, it is equal to 3.5 meters. This is the problem now. The resultant force R acting at a point E, as shown in figure, can be replaced by equal force applied at A in the same directions together with the couple now. Because yes, we have to shift that force 60 newtons to at A position now. The single force and a couple at A we require now. That is the moment of the couple is equal to, which is equal to 60 into 0.833, which is nothing but equal to 49.98 Newton meter. It is explained as like this now. Now in figure number 1, you see B now. At A, all the forces which are acting on the beam are replaced by single force R is equal to 60, which is acting 0.833 as shown in figure now. Now I have to represent the force as well as the couple at a point A now. Okay, at A, they substitute the values of forces 60 newtons in upward direction as well as the downward directions, such that the resultant force acting at A is equal to 0 now. At A is equal to 0. That is 60 newton is there now. That is equal magnitude of resultant force, but representing both the forces which are acting in opposite directions. That is at A, 60 newtons and 60 newton force both are acting in opposite directions, so that the resultant force as well as the line of action of the force is also same. Hence, the couple created by the forces at a point A is equal to 0 now. When we are putting 60 newtons now. Now, this if you take the force which is in downward directions now, this force, both are equal in magnitude and separated by certain distance now, acting in upward directions. So, these two forces tends to rotate the body in clockwise directions now. And so, when we are keeping the force at A point, a single force of 60 newtons we can keep it now, as well as the couple created by the forces which are acting at A and E also considered, which is equal to 60 into 0.833, and the direction is clockwise directions now, because it tends to rotate the body, it is also that is in the clockwise directions now. In second case, the single force, if it is shifted to point B now, what is the couple now? Again, the original figure I am taking now, the resultant force is acting at a point E now, which is at a distance of 0.33 as shown in figure. Here, D as shown in figure. Now, keep equal of resultant force 60 newtons, both in magnitude and directions. The two forces keep at B as shown in figure now. That is 60 newtons downward directions, 60 newtons upward directions now, you have to keep. That means the resultant force acting at B is equal to 0 now. Now, when we are taking the single force at a point B, that is 60, this downward force, upward force 60 newtons, which is acting here now, and downward force acting at E position. These two are equal in magnitude and acting in opposite directions. That is, they are tends to rotate the body in anti-clockwise directions. Hence, the couple at B is given by, additionally, at B, it should be equal to force into perpendicular distance between the two forces, which is equal to 2.667. This value is nothing but moment created when the force which is acting at a point E is replaced and keep it at B positions. The couple is also acted, which is equal to 60 into 2.67. This is our required answer now. So it is explained like this now. From figure number 3.16b, the distance B is equal to AB minus AE, that is 3.5 into 0.833, which is equal to 2.667. That is the distance between, here it is given, the force, it is given AB, it is E now. This distance is given 0.833. So the total distance is given, which is equal to 3.5. So the distance is equal to 2.667 meters now. Now, if the force R is equal to 60 newtons now, this 60 newton is the resultant force is acting at E point. When it is moved at a point B now, that is we are keeping here one force, the same force, one more force putting up. That is at B, RB and one more RB now. Equal to the resultant force, but both we are keeping acting in opposite direction in the same line of actions. Hence the resultant force at B is equal to 0 now. But the force which is acting at B, upward direction, this force, and downward direction at E, it always tends to rotate the body in anti-clockwise directions. Hence the couple is equal to 60 into 2.667, that is created at B when we are changing the position of resultant force from E position to B position. So it is equal to, we can take it as 60 into 2.667 meters, which is equal to 160 Newton meter. This is nothing but a couple that is acting at B when the resultant force is shifted from E to B position. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.